All right, let me show you how to do these awesome mixture type problems. This is a kind of problem which you could get a lot. Textbooks enjoy them, and actually, quite honestly, they are useful in real life. So, for example, I got this one. For a particular experiment, you need 10 milliliters of a 30% solution of hydrochloric acid, HCl. Unfortunately, all you have available is a liter of a 90% solution of HCl and a liter of a 5% solution. How much of each solution should you mix together to get 10 milliliters of a 30% solution? So, I mean, why would you need to know this kind of stuff? Well, say like you're working at a research station in Antarctica and you can't just order, you know, the exact supplies that you need. You need to make do. You need to be resourceful. So you've got, what you have available is a 90% solution, meaning 90% of the liquid is the hydrochloric acid, pretty strong, and then you've got a liter of a 5% solution, a pretty weak solution, and you need to figure out a way to mix these in the right way so that you've got 10 milliliters of a 30% solution, where 10 milliliters, where 30% of it is the hydrochloric acid. Okay, so in this is kind of an application of weighted averages, which I'll show you at a certain part in the solution of this. It should kind of look like the setup for a weighted average type problem. So, but let's just talk it out, see what we know, and kind of see if this just flows logically. Okay, so all right. So what do we know? Okay, we've got a 90%. So first of all, I'm going to instead of percentages, I'm gonna use decimals. So 90% will be 0.90, which I'll probably just start calling zero point 0.9, same thing. And then there's a 5% solution, so we'll call that 0.05. And so I'm converting the percentages into decimals so that we can actually use these in equations. So and then the 30% solution, 0.30, which I may start calling just zero point 0.3. All right, so let's name some variables. We've got the 90% solution. I'm going to call that S because that's pretty strong. Um, and then we've got the 5% solution. So I'm gonna call that W. That's pretty weak, pretty diluted. Okay. Um, so we want to mix these things together, the strong solution and the weak solution. Um, so S and W are actually going to stand for the volume of each kind of liquid. So um, a certain number of milliliters of we'll call S a certain number of milliliters of the strong solution. W will be a certain number of milliliters um, of the weak solution. Okay, so what we're gonna add these together. We're gonna mix the strong and weak solutions together. So um, so so here's how we would do it. 90% or 0.90 of the strong solution. Um, so 90. So however much we pour in of the strong solution, 90% of it will be hydrochloric acid. All right, so that's what that means. 0.90 times S milliliters is 90% of the solution will be hydrochloric acid. All right, and then we're going to add the weak solution. So zero point 0.05 of the weak solution, however much we pour in, 0.05 of it will be hydrochloric acid. And when we add this together, what we want to happen is for the final solution to be 30% hydrochloric acid. So 30% of it will be hydrochloric acid. And then we want a certain volume or a certain amount of liquid at the end. So that's going to be 10 milliliters. So 30% of 10 is what we want. So 90% of a certain liquid will be hydrochloric acid. 5% of another liquid will be hydrochloric acid. When we add these together, we want 30% of the resulting 10 milliliters to be hydrochloric acid. So that's what this is saying so far. Now, what we need to do at this point is to um, replace one of these variables because we've only got one equation here, but we've got two unknowns. You need at least as many equations as unknowns if you're going to solve it. So what from this information, we can't really write another equation that's going to tell us any useful information. Um, or maybe you can. I don't know. I didn't think about it. Here's how I would do this, and if I were you, or if you were me, or however it works, I think this is the way it should work. Okay, so let's just redescribe one of these variables. Um, let's start with the strong solution. So let's describe um, the weak solution. Actually, I said there wasn't another equation we can write here. I'm not true. I'm going to write that equation right now. So um, the weak solution plus the strong solution, or the amount of the weak solution plus the amount of the strong solution, will equal 10 milliliters, right? We're going to put a certain number of milliliters of the weak solution, a certain number of milliliters of the strong solution, and altogether we need those to equal 10 milliliters. So here's the second equation. All right, now we can use this to plug in for one of the variables. So rearrange this, solve for one of the variables, and plug that in so then we only have either W or S. I'm going to solve it for S. No, I'm going to solve it for W because I want to leave S in there. W equals 10 minus S, which means we've got 10 milliliters to work with. We're going to pour in a certain amount of the strong liquid, and then however much we don't pour in the strong, we're allowed to pour in the weak, if that makes sense. So we can just substitute this thing in for W, and then we'll just have S to deal with. So that's one way to solve a system of linear equations. Here's one equation. Here's the second. So we have a system of equations. So one way to solve is to rearrange and plug in. Another thing you do is graph both these things and see where they intersect. Yeah, you could do that, but that would take a little bit more work. So let's do it this way. So we're going to plug 10 minus S in for W. So I'm just going to rewrite this thing. So this is the part that looks like weighted averages. The solutions are counting. They have different weights. 90% of this solution is hydrochloric acid, whereas only 5% of this solution is hydrochloric acid, and then altogether it's going to be a 30% solution. Okay, so I'm substituting in 10 minus S for W. This 5 is going to look like an S. Strong. Okay, I'll just try to exaggerate the S shape. So this is an S. That's a 5. Equals. All right. So let's just kind of clean this up a little bit. I'm gonna call that 0.9 S plus. Okay. 0.05. So we got to distribute this 0.05. So we've got 0.05 times 10 is 0.5, and then 0.05 times negative S is negative 0.05 S equals 0.3 times 10 is just 3. All right. So, and let's go ahead and subtract this 0.5, get it over there. So we've got 0.9 S minus 0.05 S is equal to 2.5 milliliters. Sorry about that. Okay, then 0.9 minus 0.05. 0.9 minus 0.05. Just doing that calculator. Um, to save some thought. This is a long lesson, and I'm starting to space out. Okay, 0.85 times s is equal to 2.5. Now we can divide both sides by 0.85. So the strong solution, so 2.5 divided by 0.85 is equal to 2.94 roughly. So we want now I'm rounding to make this easier. If you're a scientist in the field and you know you need to be precise, don't round it as much as I'm rounding it. Okay, so we want 2.94 milliliters of the strong solution. So what we need, so we want that means so the weak plus the strong is, or the weak solution is the 10 milliliters minus the strong. Um, so how much of the weak solution do we want? It would be 7.06 milliliters. Yeah. So this is how much of each solution we want. If we add these together, we'll get a 10 milliliter solution that's 30% hydrochloric acid. So that's your basic mixture problem, and you know, basically set up two equations, um, and then you can substitute it in and then solve. All right, good luck.